Good morning, students. So, our topic for today's discussion are lenses. Lenses are basically a piece of transparent refracting material. Usually, we make use of glass for that, which is bound by two surfaces. Now, when we combine mirrors together, what we get are called lenses. In your book, they have discussed two major lenses. They are convex lens, also called converging lens, that is the first one, convex lens or converging lens, and second is concave lens or diverging lens. As you can see in the first lens, the convex lens, it is bound by two spherical surfaces. If we take two convex mirrors and we bind them together, they are bound together, what we get is a convex lens. As you can see, we have two surfaces. One is this one, that is a convex mirror, and this is the second convex mirror. They are joined together. What do they form? A convex lens. A convex lens is one which is thick in the middle and thinner at the edges. Okay, a convex lens is, it is thick at center and thinner at edges. As we can see that this kind of lens, it is thick at the center and it is thinner at the edges. That is called a convex lens. It is also called a converging lens. Why it is called converging lens? Because it converges or collects all the parallel rays to one point. Suppose if this is the principal axis and if you're taking the rays which are parallel, they are collected to a point. Which point would that be? That is the focus. Okay, so all the parallel rays are collected at one point called the focus. That is why convex lens is also called a converging lens. Since lens is bound by two surfaces, so a ray of light while going through lens refracts twice, it bends twice. As we did in the glass lab also, there was refraction taking place at two surfaces. In case of lens also, since we have two surfaces, so there will be double refraction of the light while passing through a lens. The second lens is a concave lens. Concave lens, as you can see, it is bound by two spherical mirrors. Which mirrors are we talking about? Concave mirrors. Okay, so here we have two concave mirrors. When they are joined, bound together, they result in formation of a concave lens. Concave lens is the one which is thinner in middle and thicker at edges. Right, in the middle it is thinner as compared to the edges, it is thicker at the edges. It is also called a diverging lens. Why diverging? Because it will diverge the parallel rays so that they are scattered. If we have these parallel rays like this, they are diverged so that if produced backward, they appear to intersect at the focus. Okay, so since a convex lens converges or collects all the parallel rays to one point, it is called a converging lens. And concave lens scatters the beam of light so that the rays, they are scattered, dispersed, and if they are produced backward, they appear to be coming from the focus. That is why it is called a diverging lens. I said here that we made use of two spherical mirrors. We can also make use of one plane and one spherical mirror, right? Like if I make use of one plane mirror and the other mirror which I am using here is convex, so this is called a plano-convex lens. These kind of lenses are also used where both the surfaces are not spherical, one of it may be a plane one. If I use one surface plane and the other concave like this, that is called plano-concave lens. If this is our lens, suppose we are talking about convex lens, then the aperture of lens, first term is aperture. Aperture is the diameter of the circular edge of lens. If this is a lens which is bound by two spherical surfaces, let us say P and Q, Then this diameter AB, what is that? That is called the aperture. So aperture is basically diameter of circular edge of lens. So diameter of circular edge of lens is called aperture. Second is center of curvature. Since in case of convex and concave mirror we have two spherical surfaces, so naturally it will be having two center of curvature. So in this case, if I take P as my first spherical, let me draw this diagram again. Okay, so this was our aperture. If I take, this is P and this is Q surface, this is P, if that will, the sphere will be completed on this side now, so we can say that here will be a center of curvature. Since we have two center of curvatures for two surfaces, we will be using subscript C1 and C2. First of all, we will take a straight line which is passing through the center. Which center is this central point is denoted by C, and this capital C is called the optical center. See, in mirrors, C stands for center of curvature, but here capital C means optical center. It is also called optical focus sometimes. Optical center has a property that the light ray which is passing through optical center passes undeviated, that is, it passes straight. No refraction of light takes place from this point. Okay, so we were talking about two center of curvature. If P is our first spherical surface and if we complete this sphere, this will be the center of curvature for P surface, because center of curvature is basically if we make a sphere of glass and we cut a mirror out of it, that is called spherical mirror, right? So if we are talking about P here, and if I complete this sphere like this, so this will be the center of curvature for that I denote by C1. Now I take the second surface, Q surface, like this. So the sphere will be completed like this here. Okay, that will also have a center of curvature. We denote it by C2. So a spherical lens, since it is bound by two spherical surfaces, it will have two center of curvatures which we denote by C1 and C2. Similarly, if we have a concave lens, that will also have two center of curvature. This is our concave lens. This is our principal axis passing through optical center. If P dash is my first surface, here will be the center of curvature for this. I am denoting it by C1 dash. Q dash is my second surface. The center of curvature will be C2 dash. Okay. Now center of curvature will be on which side of principal axis depends that which spherical mirror we are talking about. Okay. Okay, after that optical center I have told you, then is principal focus and focal length. First I am talking about convex lens. Principal focus, now we will have two focus, that is called foci. We have foci for lens because we have two mirrors, so naturally there will be two focus. Okay, for understanding that, for understanding the first principal focus, I am making a convex lens. This is my straight line passing through the optical center. So first principal focus, first principal focus is the position of point on principal axis for which image by lens is formed at infinity. If I say the position of the object is at f1, parallel rays will start from here. This is our aperture. Parallel rays will start from here. Then what will it do? It will make these rays parallel to principal axis. Similar in mirrors, a ray which passes through principal focus becomes parallel to principal axis, and the ray which is parallel to principal axis passes through focus. So first principal focus is the position of the point object on principal axis for which the rays become parallel to principal axis, that is image will be formed at infinity. Distance of this focus from optical center is called the focal length. This is also the first focal length, that is why we use f1 here. How will we find the second focal length? Again I am making a convex lens. optical center, this is my aperture. They say second principal focus of a convex lens is position of the image point on principal axis when the point object is situated at infinity. Here if the rays are coming from infinity, all the parallel rays are collected where? At the focus to form the image there. So this is our second focus. Second focus is the position of the image when the object is situated at infinity. This is the second focal length, distance between second focus and center of optical center. Okay, I'm repeating again what is f1 and f2. If we talk about convex lens here, this is our convex lens. F1 is the position of the point object, that is first focus is the position of point object for which the image will be formed at infinity because the rays are becoming parallel here, and distance of this first focus from optical center is called the focal length, denoted by F1. Similarly, if we talk about second principal focus, second principal focus is the position of the image when the object is situated at infinity. Here the rays are coming from infinity, they're collected to a point after passing through the lens, that is called the second principal focus. So distance of the second principal focus from the center is called the focal length. Okay, so generally if they ask you about focus, we will have to define both the focus here, right? Because we have two focus and we have two focal length for the lenses. Then again about concave lens, if we talk about, we will be having two focus and two focal length. For that, if I take a concave lens, okay, this is my optical center. So first principal focus for concave lens is virtual position of the point object on the principal axis for which the image formed by concave lens is infinity. We are taking it parallel to convex lens only. It is the position of the point object, but virtual position for which the image will be formed at infinity. If we take the rays which appear to be passing through focus, because it is a diverging lens, so it will diverge the rays, right? The rays will not actually intersect at focus, such that the image is formed at infinity. It makes them parallel to the principal axis, right? So f1 is the position of the point object, virtual position for which the image will be formed at infinity. And what will be this distance between center of curvature and f1? That will be the first focal length. Similarly, second principal focus is the position of the image point. Second principal focus is the position of the image point on principal axis when the point object is situated at infinity. Now the rays are coming from infinity, they are parallel, they will be diverged such that the image appears to be formed at f2, that is our second focus. If we take parallel rays, the rays will be diverged. If we produce them backward, they appear to be intersecting at second focus, they appear to be forming an image here. Distance between the second focus and center of and the optical center is the second focal length. Okay, so this is how we define first, second focus and first and second focal length for convex and concave lens. For better clarity, you can watch the videos again, okay, because these are new concepts for you. Okay, after that we have rules for drawing the ray diagram. First rule says a ray of light passing parallel to principal axis will pass through focus after refraction. That is correct. That is what we have shown here also while drawing the focus, that the ray which will be parallel to principal axis, the ray which will be parallel to principal axis will always pass through focus after refraction. Second, a ray of light which is passing through focus becomes parallel to principal axis. This is also correct. A ray which will be parallel to principal axis ray which is parallel to principal axis after refraction will a ray passing through focus will become parallel to principal axis. Third, a ray of light which is passing through optical center passes straight without any deviation. Let us see that once. First was a ray of light which comes in a direction parallel to principal axis. The first ray, this is our optical center which is parallel to principal axis. Where will it pass through? After refraction will pass through the focus. Second rule said a ray of light which is passing through the focus, passing through the, this is focus, passing through focus after refraction becomes parallel to principal axis. Third rule says a ray of light which passes through optical center, it will pass undeviated. Similar rule applies to concave lens also, right? Shall we see that as well? Okay. First rule said a ray of light in a direction parallel to principal axis. So this is our concave lens. This is our optical center. Now this ray is parallel to principal axis, but it will be diverged. If we produce it backward, it appears to pass through the focus. Second rule says a ray of light which is directed towards the focus, it will not actually pass because it is a diverging lens, diverging, made up of diverging mirrors. So here what will happen, it will become parallel to principal axis. Third says a ray of light which passes through optical center, that will pass undeviated. Through optical center there is no refraction, no deviation of light. Okay, so that would be all for today. Next time we will be doing image formation for concave and convex lens. Thank you so much.